Welcome to the new era of video creation with Baozai 8. Today we will discuss handle class imbalance in a dataset. How do you handle class imbalance in a dataset, and what strategies do you use to improve model performance in this scenario? Class imbalance occurs when the distribution of data across classes is not uniform, i.e., one class has a significantly larger number of samples than the others. This issue is common in real-world datasets such as fraud detection, where fraudulent transactions are much rarer than legitimate ones, or medical diagnostics, where certain diseases or conditions are less frequent. The primary problem with class imbalance is that most machine learning algorithms are biased toward the majority class. This can result in poor generalization for minority classes, leading to low recall or high false negatives for those classes. For example, in fraud detection, a model may predict that all transactions are legitimate, achieving a high overall accuracy, but failing to identify fraudulent transactions. Understanding and addressing this issue is crucial for creating models that perform well across all classes. To handle class imbalance, there are several well-established techniques. Resampling methods involve either oversampling the minority class, adding more copies of the minority class examples, or undersampling the majority class, removing some of the majority class examples, to achieve a balanced dataset. However, oversampling can lead to overfitting, while undersampling can result in the loss of important data. SMOTE is a more advanced technique for oversampling, where synthetic data points are generated by interpolating between existing examples from the minority class. This helps provide a more diverse set of examples for the minority class without duplicating existing ones. Cost-sensitive learning modifies the learning algorithm to account for the class imbalance by applying higher penalties to misclassifications of the minority class. This encourages the model to prioritize correct predictions for the minority class. Class weight adjustment changes the loss function so that errors on the minority class have a larger impact on the model's overall loss. Many modern algorithms like XGBoost or logistic regression allow for class weighting. In addition to resampling techniques, certain algorithms are inherently more suited to dealing with imbalanced datasets. For example, tree-based algorithms like random forests and XGBoost allow for class weight adjustment, where you can penalize misclassifications of the minority class, making the model more sensitive to these examples. Ensemble methods like bagging and boosting are useful for improving performance when dealing with imbalanced data. Boosting algorithms like AdaBoost or XGBoost increase the model's focus on harder-to-predict minority class samples by iteratively adjusting the weights of incorrectly classified samples. For SVMs, the C parameter can be adjusted to apply a higher penalty for misclassifying minority class examples, which improves the model's sensitivity to the minority class. In extreme cases of class imbalance, you might use anomaly detection models like one-class SVM or isolation forest, which are designed to detect rare or outlier instances, which may align with the minority class. When evaluating models trained on imbalanced datasets, accuracy is not the most appropriate metric. In the case of highly imbalanced data, a model that always predicts the majority class can achieve a high accuracy, but still fail at correctly identifying minority class instances. Therefore, the following evaluation metrics are more effective. The precision recall curve focuses specifically on precision, the percentage of correctly predicted positive instances, and recall, the percentage of actual positives that were correctly predicted, both of which are crucial in imbalanced scenarios. The F1 score is the harmonic mean of precision and recall, providing a single value to assess model performance. This metric is particularly useful because it balances the trade-off between precision and recall. The area under precision recall curve, AUPRC, is often a more informative evaluation metric than the AUC-ROC when dealing with imbalanced datasets, as it specifically emphasizes how well the model performs with respect to the minority class. One of the most commonly used techniques for addressing class imbalance is SMOTE, synthetic minority oversampling technique. Unlike simple oversampling, where you replicate minority class samples, SMOTE creates synthetic data points by interpolating between existing samples from the minority class. For example, if we have two minority class instances, SMOTE will create new synthetic instances that are linear combinations of those two. The main advantage of SMOTE is that it reduces the risk of overfitting compared to plain oversampling, as the model sees diverse synthetic data points instead of repeating the same minority class examples. However, SMOTE can also introduce some disadvantages, such as the creation of noisy data or outliers, especially if the interpolation process leads to points that do not represent the true distribution of the data. Hence, it's important to apply SMOTE carefully and validate the results using robust evaluation metrics. Ensemble techniques are another effective approach for dealing with imbalanced datasets. Here are some techniques specifically designed to improve performance in these scenarios. Balanced random forest is a variation of the traditional random forest, where each tree is trained on a balanced bootstrap sample by undersampling the majority class, ensuring that the minority class is adequately represented during training. Easy ensemble and balance cascade are ensemble methods that generate multiple models by iteratively undersampling the majority class and training classifiers on these balanced subsets. These methods improve model performance by focusing on minority class examples during each iteration. Boosting algorithms, such as ADA Boost, improve the model's focus on misclassified instances. As the model iterates, it applies more weight to difficult-to-classify minority class instances. Stacking models involves combining multiple different classifiers with distinct biases to create a meta-model, which helps reduce overall prediction error. Cost-sensitive learning is another effective strategy for handling class imbalance. The core idea is to adjust the cost function to assign a higher penalty for misclassifications of the minority class. By incorporating misclassification costs, models can be trained to prioritize the correct prediction of the minority class, even at the expense of the majority class. Many machine learning algorithms, such as XGBoost, logistic regression, and SVMs, allow you to adjust class weights or apply penalties to specific classes in the loss function. By increasing the cost for misclassifying minority class samples, you guide the model to be more sensitive to those instances and reduce bias toward the majority class. However, this approach requires careful tuning of the cost function, as overpenalizing the minority class can lead to overfitting and poor generalization. Therefore, cross-validation is critical in determining the appropriate cost adjustments. Evaluating a model trained on an imbalanced dataset requires more than just the accuracy metric. Instead, focus on a set of metrics that provide better insight into how well the model handles the minority class. Stratified k-fold cross-validation ensures that each fold of the dataset used in cross-validation maintains the proportions of minority and majority classes. This prevents biased evaluations. Precision recall AUC is a more informative metric than AUC ROS in the case of class imbalance because it directly assesses the model's ability to predict the minority class accurately. A confusion matrix helps to visualize false positives, false negatives, and correct predictions, allowing you to assess model performance in terms of the minority class specifically. Additionally, consider domain-specific metrics like balanced accuracy or macro F1 score to ensure that the evaluation metrics align with the application requirements. Once a model is deployed, it's important to monitor its performance over time. Changes in data distribution or underlying patterns, referred to as concept drift, can degrade performance. Model drift occurs when the relationships between input features and target labels change over time, which is common in real-world applications like fraud detection or healthcare. Retraining models is a common practice to ensure the model adapts to new data. Periodic retraining helps keep the model in sync with the latest trends. Building a feedback loop can also help the model evolve over time by using real-world data to adapt to changing conditions. Drift detection systems can identify early signals of concept drift, allowing for timely retraining before performance degradation becomes significant. In summary, addressing class imbalance is crucial to developing models that perform well across all classes. Key takeaways include techniques such as SMOT and undersampling help balance class distributions. Cost-sensitive learning and class weight adjustments help improve performance for minority classes by altering the learning process. Evaluation metrics like precision recall curves, AUC, and cross-validation should be used to ensure the model generalizes well to the minority class. By understanding and applying these methods, you can build more effective and robust models for imbalanced datasets.